Today we are going to talk about helicopters, their history, operating principle, and much more. Don't forget to subscribe, like, and share. As the main rotor spins, an opposing force is generated, tending to rotate the fuselage in the opposite direction. To neutralize this effect, a tail rotor is added. This way, the helicopter achieves stability and directional control, revealing its unique versatility in hovering and vertical takeoff. The main rotor, composed of long aerodynamic blades, functions as a rotating wing. Each blade has a profile similar to an airplane wing, designed to generate lift as it moves through the air. As it rotates, a pressure difference is created between the upper and lower surfaces of blades, resulting in vertical thrust. The pilot controls ascent or descent by adjusting the collective pitch, the uniform angle of attack of the blades. When pitch increases, lift grows, allowing vertical takeoff. The rotor spins thanks to a central engine, usually a turbine, connected by a shaft to the rotor assembly. This system demands extreme mechanical precision. Any failure can compromise flight safety. The engineering behind the rotor is a synthesis of aerodynamics, centrifugal force, and fine power control. Yaw! Pitch and roll. To steer the helicopter, the pilot uses three main controls: collective, cyclic, and pedals. The collective, as noted, alters the pitch of all blades equally, regulating altitude. The cyclic, in turn, changes the blade pitch cyclically during rotation, creating lift difference on one side of the rotor disc. This tilts the helicopter forward, backward, or sideways. The pedals control the tail rotor, adjusting yaw, the rotation of the fuselage around its vertical axis. This triple coordination requires constant attention from the pilot because, unlike airplanes, helicopters are inherently unstable. Flying a helicopter is like balancing on a beach ball in the air. Neutralizing unwanted rotational forces and keeping direction under control is fundamental. The torque generated by the main rotor tends to rotate the helicopter opposite the blade rotation. The tail rotor, powered by a shaft from the main transmission, produces a lateral force to counterbalance this torque. In tail rotorless models like Rotor helicopters, this effect is achieved through lateral air jets or embedded rotors. Stability also depends on the center of gravity and weight distribution. Gyroscope sensors, accelerometers, and electronic stabilization systems are increasingly used to smooth commands and facilitate manual control, especially in hover flights. Constant pilot correction is essential to avoid oscillations and ensure safe airborne positioning. The advancing blade encounters more air and generates more thrust than the retreating blade. To correct this, articulation mechanisms on the blades, known as flap and feathering, automatically adjust the pitch. Forward translation enables higher speeds and aerodynamic stability, but also requires constant adjustments. It is a transition between vertical flight and conventional flight. Controls must be accessible, and wide external visibility is essential for landing maneuvers in confined environments. Many helicopters include multifunction displays, glass cockpits, and audible alerts. Communication systems allow constant contact with control towers and other aircraft. Safety also depends on reinforced seats, 5-point harnesses, and armor when necessary. Everything converges to ensure safe and precise flight control. A helicopter structure must combine lightness with strength. Fuselages are generally made of aluminum alloys, carbon fiber composites, or titanium, materials that offer rigidity and impact absorption. Rotor blades are especially critical and require internal reinforcements and perfect balancing. Cargo compartments, reinforced doors, and retractable landing gear are optimized depending on usage, civil, military, or rescue. In hostile operations, light armor is added. Emergency flotation systems are installed on naval helicopters, and fuel tanks are designed to avoid explosions. Thermal sensors, cameras, and autonomous navigation systems enhance efficiency and safety in any condition. Structural durability is ensured through regular inspections and rigorous maintenance. Everything is calculated so the aircraft can withstand extreme vibrations, hard landings, and sudden directional changes. Structural engineering transforms a helicopter into a safe capsule between sky and earth. The helicopter's engine is its heart. In modern models, gas turbines replace piston engines, offering more power and efficiency. The turbine draws in air, compresses it, mixes it with fuel, and ignites it, generating a gas flow that spins the output shaft. This shaft drives the transmission box, which transfers rotation to the main rotor and tail rotor. Engine efficiency depends on altitude and ambient temperature, requiring automatic adjustments. Many helicopters use FADEC systems, full authority digital engine control, which monitor all parameters in real time, optimizing performance and preventing failures. Redundant fuel systems and filters ensure stable operation even under adverse conditions. An engine failure can be mitigated by auto-rotation, a critical emergency maneuver. Thus, propulsion is more than power. It's precision and resilience under any condition. In case of total engine failure, the helicopter doesn't fall immediately. Thanks to auto-rotation, the rotor keeps spinning from upward airflow, allowing a controlled descent. The pilot adjusts the collective pitch to maintain blade rotation. Near the ground, the pitch is briefly increased to slow the fall, the flare. This maneuver requires constant practice and depends on available altitude and speed. Helicopters also feature visual and audible alarms for fire, low hydraulic pressure, or electrical failures. Automatic fire suppression systems, circuit duplications, and hydraulic accumulators are installed as redundancies. Pilot emergency preparation involves frequent simulations and training in realistic simulators. Flight safety results from a combination of reliable technology, quick human response, and advanced planning. Every emergency requires fast yet trained action, almost instinctive. The helicopter is one of the most versatile aircraft in history. In the civil sphere, it is used for executive transport, aeromedical rescue, firefighting, construction, and tourism. It can land in remote or congested areas where planes could never reach. In the military sector, its utility expands. Medical evacuation, tactical transport, aerial attack patrol, and reconnaissance. Each function demands specific adaptations. Armor, weaponry, infrared sensors, or anti-jam systems. Modularity allows rapid reconfiguration. Helicopters like the Black Hawk, Apache, or Super Puma have become icons of this multifunctionality. In policing, they serve as aerial surveillance platforms. In agriculture, they spread fertilizers or pesticides with precision. The ability to hover, fly low, and maneuver in 3 dimensions makes the helicopter unique. Its contribution to society is as diverse as it is essential. In the countryside or the city, in peace or conflict, it responds where others cannot, and often it's the first to arrive. Modern helicopter navigation systems use GPS, INS, inertial navigation system, and integrated digital maps. This allows precise flights even in adverse weather or areas without visual references. Autopilot systems adjust altitude, heading, and speed, reducing the pilot's workload. In long or complex missions, these features are crucial. Navigation in urban environments requires additional sensors, such as proximity radar and thermal cameras. To avoid obstacles, drones inspire the development of experimental autonomous helicopters, programmed for tasks like deliveries or surveillance. Integration with communication networks enables real-time data exchange, optimizing routes and emergency response. The constant advancement of these systems redefines a pilot's role and expands the helicopter's potential in previously unthinkable tasks, with greater precision, fuel economy, and operational safety. Some models eliminate the tail rotor by using alternative configurations such as coaxial rotors. Two sets of blades rotating in opposite directions on the same vertical axis, or tandem, with two horizontal rotors in series. Coaxial helicopters, like those from Camel, offer greater stability, efficiency, and load capacity as they internally cancel torque. Tandem helicopters, like the CH-47 Chinook, distribute weight longitudinally, making them ideal for heavy transport. These configurations improve aerodynamic efficiency and reduce the runway length required for takeoff and landing. However, they demand more complex transmission systems and greater mechanical precision. The configuration choice depends on mission needs and operational limitations. Helicopter design is a constantly evolving field, and these alternative configurations expand performance and application possibilities without compromising the aircraft's signature maneuverability. A helicopter's lifespan depends directly on rigorous maintenance of the components. Each part has a maximum operating time, known as TBO, time between overhaul, after which it must be replaced or overhauled. Blades, engine, transmission boxes, and hydraulic systems are frequently inspected. Technicians use methods like ultrasound, x-rays, and borescope inspections to detect cracks or wear. Modern software assists in predictive maintenance control, alerting for replacements before failures occur. Beyond scheduled maintenance, inspections follow every flight, and deep overhauls occur after a defined number of operational hours. Mechanic training is constant and rigorous. A well-maintained helicopter can operate safely for decades. Neglecting maintenance, on the other hand, compromises aircraft integrity and crew safety. Operational longevity stems from technical discipline and continuous commitment to excellence. Helicopters face unique challenges in extreme environments. At high altitudes, thin air reduces lift and engine efficiency, requiring more powerful turbines. In deserts, sand particles wear down blades and engines, demanding additional filters and protections. In polar climates, ice may form on blades and surfaces, affecting aerodynamics. Therefore, de-icing systems using electric heating or hot air are employed. At sea, naval helicopters need reinforced landing gear, floats, and automatic stabilization systems to land on moving decks. Each scenario requires specific adaptations, from corrosion-resistant paint to structural reinforcement. Extreme performance proves the robustness of design and the quality of the engineering involved. The most difficult missions are those that reveal a helicopter's true capability. The next generation of helicopters incorporates hybrid propulsion, tilt rotors, and artificial intelligence. Aircraft like the Bell V, 280 Valor combine vertical versatility with airplane speed. Electric projects promise to reduce noise and carbon emissions. Autonomous systems are already being tested for medical evacuations and urgent deliveries. Smart materials and self-repairing structures are in development. Connectivity with 5G networks will allow real-time communication with command centers and other aircraft. Additionally, the fusion between helicopters and drones creates a new category of aerial vehicles, light, accessible, and multifunctional. The urban sky of the future could be populated by silent, efficient air taxis. The evolution of the helicopter is constant, driven by humanity's need to surpass limits. Vertical flight will become increasingly precise, safe, and sustainable, and will continue changing how we connect with the world.